Hi. I'm going to talk to you today about an issue that lives at the nexus of energy production, environmental stewardship, and public health: the safe disposal of radioactive materials. Nuclear power has helped to reduce greenhouse gas emissions while maintaining the world's energy production needs over the last half-century. Nuclear power is clean and efficient compared to conventional power generation methods such as coal, which still comprises approximately 38% of the world's annual electricity budget. While nuclear power is widely utilized in some countries, such as France, where approximately 75% of their annual electricity budget is derived from nuclear power generation alone, and has made them the largest electricity exporter in the world, grossing over 3 billion euros annually on electricity exports alone, there yet remains a real social and scientific issue with nuclear power generation. That issue, of course, what do we do when the fuel is spent? Gasoline is easy. You burn it, it goes into the atmosphere, you forget about it. It's a problem for the next century. Right. Nuclear power and its associated waste presents a much more apparently imminent threat to public health, and one that may persist for what the layperson may effectively consider to be eternity. We can't put it in the sky, can't put it in the ocean, we can't shoot it out into space. So we have to deposit our radioactive waste materials in subsurface repositories, which have been rigorously characterized and engineered to be able to safely store these materials for thousands of years. The project that I have been involved with here at Los Alamos, and in collaboration with the Geological Survey of Israel and the Negev Nuclear Research Center, revolves around the characterization of one such potential repository location in the Negev Desert of Israel. There are some aspects about the location that are immediately attractive. It's remote, it's arid, it has a deep water unsaturated zone, and furthermore, local geology indicates the potential existence of a natural geologic barrier to radionuclide migration. Of course, it's more complicated than just burying trefoil-marked barrels leaking lime green sludge in the middle of the desert. We have to understand the attitude of the subsurface, the orientation, thickness, and lateral heterogeneity of the rocks or stratigraphy in the area to understand and identify any obstacles that may preclude the emplacement of a waste repository in the Negev. So to understand the tectonic and stratigraphic evolution of the southern margin of Israel, which is key to understanding the subsurface of the Lebanite margin, which is the southern margin of Israel, we have to understand the tectonic and stratigraphic evolution of that area of the world over geologic time. So referring to the paleogeographic map behind me, you can see the world was a very different looking place 270 million years ago. The area of the world that would become modern-day Israel was undergoing extension as tectonic plates rifted apart during the opening of the Neotethys Sea. This proto-Mediterranean basin is the paleodepositional environment in which our natural geologic barrier would be formed over the following 175 million years of geologic evolution. A process which can be accurately modeled conceptually, of course, through the building of a submarine sandwich. You start with a hoagie roll, the Earth's lithosphere. As you extend the lithosphere during the Mesozoic, you're opening a basin and creating accommodation space for our constituent layers inside. While the roll is opening, we're depositing our porous marine ingredients into the basin: lettuce, red onion, tomato. 95 million years ago, rifting ceases, and we begin the slow process of closing the sandwich, a task that would take our imaginary sandwich artists around 65 million years to accomplish. All the while, we're depositing our shell marine ingredients into the basin: mayonnaise, Swiss cheese, ham, roast beef. The tectonic compression involved with closing the sandwich is deforming our ingredients over geologic time, resulting in a tectonic fabric of folds and faults, creating a complex and varied flavor to consider. Now, as I'm sure you can imagine, our constituent layers of meat, vegetable, cheese have distinct mechanical and chemical properties. Geochemical experiments carried out here at Los Alamos have observed that our shallow marine ingredients are composed of low and high permeability layers with a proven capacity to absorb actinides, forming the basis of our natural radionuclide barrier. Like radioactive mustard attempting to penetrate the ham on your sandwich, it forms an effective barrier to the contamination of the undisturbed mayonnaise beneath. Similar to the WIPP waste site here in New Mexico, constructed in the thick evaporites of the Delaware Basin, the geology is critical. In the event of an engineering failure, the migration of mustard throughout our lunchbox must be impossible. As we continue to refine our geologic models of the Negev, our future undertakings are focused on integrating hydrologic models for flow and transport to define possible radionuclide migration pathways in the system, with our ultimate goal being that one day our sandwich will provide a safe place to house radioactive mustard as nuclear power progresses to serve the world's energy needs. Thank you.